All right, now we will discuss one-dimensional wave interference. And we're going to do it 3 different ways. And it's all math, so hang on. So this is just a reminder. So this is our displacement equation. And this is called the phase. So if we want to, we could write it A sine phi if we wanted to. All right, here we go. And I'm going to say this three times, right? Because again, we're doing it 3 different ways. So you're going to see this again and again and again. So here we have 2 waves, number 1 and number 2. They are identical, except they have different phase constants. So what am I talking about? Same amplitude, same wavelength, right? This is the wave number, same frequency, right? So the same waves, just different phase constants. And look at it, they're traveling the same direction. All right, now, what am I talking about, different phase constants? It just means they have different starting times. So let's say that this one is like that, and then this one started later, so maybe it's like that. Okay? So it's supposed to be identical, but they have different starting times. So that's what it means, okay? Same everything except for different starting times, different phase constants. So what we want to do is we want to see how these guys are going to interfere. All right? That's what we want to do, mathematically. How are they going to interfere? All right, so the first time, all right, so I said we're doing it 3 ways. So this one is what I call qualitative. That means we're just going to kind of wave our hands, not do a whole lot of math, but some. And then, all right, and then we'll get into the math in a couple of minutes. All right, so here we go. So here's the net displacement. Just you add them, right? Superposition, just add them. So you have A sine phi 1 plus A sine phi 2. Whoopee! Right? Okay. So let's do the easy ones. What do you say? So let's say that phi 1 equals phi 2. So that means that these guys would be the same, right? All right. So if phi 1 equals phi 2, what would be the net displacement? Well, that's kind of a silly question, right? Well, that means that this equals that. So that means this equals that. So you just add them. Whoopee! I mean, right? So, you know, so the net displacement, you just add them. So you get 2A sine phi 1. Right? That wasn't all that great, right? Now, hold on. Okay, so if these are equal, what's the phase difference? Well, Brother Weber, it's another silly question. If they're equal, what's the phase difference? There is no phase difference. Oops, sorry. Right? There is no phase difference. Okay. So here's some terminology. If there's no phase difference, and we're just adding them, are the waves in phase or out of phase? Well, that's called being in phase. And so what kind of interference? Constructive or destructive? Well, it's obviously constructive, right? We added them, so it's constructive. All right, so a couple of new words for you, or terms. In phase, and we were talking about constructive interference. All right, next case, another easy one, right? So now there's a difference, but it's a difference by 2 pi. So the phases differ by 2 pi. What's going to be the net displacement? Well, come on, what do you know about sine? You know, the sine of x equals a sine of x plus 2 pi, right? Because the sine is periodic in 2 pi, or 360, or whatever you want to call it. Okay? So what's the answer? Same as this answer. Agree? Because of that. So again, you just get that. Okay? And then, what would it be if this was 4 pi? If that were 4 pi, it'd be the same answer, because sine is periodic in 2 pi. Okay, so again, this is in phase, and you're going to get constructive interference. All right, now you know what's coming, I'm sure. We did the same, and then we had them differing by 2 pi, 4 pi, 6 pi, 8 pi. So what do you say we do one in between? All right, so now the phases differ by pi. All right, the phases differ by pi. So just use your knowledge of trigonometry. If the phases differ by pi, what are you going to get? 0, right? 0. Why is that? Well, you know why that is, right? Because the sine of x equals minus sine x plus pi. Right? Agree? Okay. So, therefore, what's the displacement? 0. Okay. So, are the waves in phase or out of phase? Well, they're out of phase. That's what we mean, right? They cancel each other. So, it's called out of phase. What kind of interference is that? It's destructive. All right? Destructive. Okay. And then we could go everything in between, but we don't want to bother. So, basically, so constructive interference, destructive interference. Phase difference is 0. Phase difference is 2 pi or 4 pi or 6 pi. Phase difference is pi. So, the type of interference, constructive or destructive, what does it depend on? Phase difference. All right? The type of interference depends on the phase difference. Again, 0, 2 pi, pi, and everything in between. Okay? So remember last chapter, right, we talked about phase difference just briefly, and I said we would talk about it in the next chapter. Well, here we are. Okay? All right. Now, this is all fine, you know, but it's all kind of like theoretical, right? In the real world, how do we make a phase difference between two waves? That's what we've got to think about. How do we actually do it, you know? Under what situations will we have a phase difference between two waves, two identical waves? So here we go. All right, so let's say we have the same starting points. So, right, so the same starting points. So we say that x equals, the change in x is 0. By the way, there's a name for that, which we're going to use a lot. Same starting points, so we have 0 path difference, okay? We're going to use that a lot. Path difference. There is no path difference, okay? But what we're saying, though, is that the sources are out of phase. So we're saying that the phase difference is pi. And you can see that, right? Here's an up, and here's a down. So when these guys interfere, they're going to cancel, agree? So you're going to have a destructive interference. All right, so that's one way to introduce a phase difference. Okay, we have different phase constants. Simple as that, right? We set these speakers up to have different phase constants. And for this one, we had pi. All right, so there's one. All right, just have the sources out of phase, right? Sources are out of phase. No path difference. No path difference, but different phase constants, so different phases. Okay, here's another way. Okay, this time, let's say it has the same phase constant, right? So they're both nice sine, right? Both sine. So that's the same phase constant, but let's make a path difference. Let's start this guy out, you know, here, and this guy here. So it's like a half wavelength. Well, if we have same sine wave, but they're a half wavelength apart, what's going to happen? Destructive interference, right? Okay, so for this one, there's no phase constant difference, right? Because they both start out exactly the same, both sine waves. But we introduced a path difference, different starting points, so non-zero path difference, right? Non-zero path difference. Okay, so that's another way we can introduce a phase difference. We can just start them out at different. Okay, so this one, okay, so the one we just talked about, we had same starting point, different phase constants. This one, we had same phase constants, different starting points. So what's the third one? Let's make different starting points, different phase constants, right? So the third one is different starting points. So we have a non-zero path difference, and we have different phase constants. See, this starts out like a sine. This starts out like a cosine, which is a sine just shifted, right? All right. So there's 3 ways we can get a phase difference. 3 ways. Okay, 3 ways to get a phase difference. Same starting points, different phase constants, different starting points, same phase constants, and then different starting points, different phase constants. Right? That's all. And that's the only way you can do it. All right. All right. So I have some good questions for you now. Two rays of light with wavelengths of 600 nanometers reflect from glass surfaces separated by 150 nanometers. The rays initially are in phase. Okay. What is the path length difference? In other words, one travels a certain amount. The other one travels a certain amount. What's the difference? How far do they travel? What's the difference? So pause your video and figure it out, please. All right? Okay, look. This guy had to travel from here to here, whereas this guy didn't, right? This wave. So this wave traveled 150 nanometers plus 150 nanometers more than this guy. So the path length difference is the 300 nanometers. Make sure you understand that. It's important. Okay, now the follow-up is when they have cleared the reflection area, the rays are going to be what? So pause your video and figure it out. Okay, we're back. All right, now think about it. The path length difference, so the path length, or delta x, whatever you want to call it, was 300 nanometers. Now, I made up this problem to be nice. Look at the wavelength. The wavelength is 600 nanometers. Now notice it says that the rays are initially in phase, right? They're initially in phase when they started off. But then they have this path difference of 300 nanometers. Now what's 300 nanometers? 300 nanometers is half a wavelength, right? So if there's a path difference of a half a wavelength, what's going to happen? I hope you understand by now. They're going to be exactly out of phase, and it's going to be destructive interference. All right, here's another one. Okay, two loudspeakers are spaced 1.5 meters apart. Both speakers emit identical, I'm being nice again, 343 hertz waves with a velocity of 343 meters per second, speed of sound, huh? And they're in phase, all right? The interference at point A is what, all right? So this point here is midway between this speaker and this speaker, and this is 2 meters away from this line. So pause your video and figure it out. Okay, we're back. All right, now look, it says that both speakers emit the same wavelength, the same frequency, and they're in phase. So if they're going to be, so the only thing that is going to make a phase difference is a path difference. But however, this distance is the same as this distance, and this distance is 2, so that means that this is equal to that. Agree? So this is the path length for this guy. This is the path length for this guy. So aren't these path lengths the same? Yeah! So the path lengths are the same. They're in phase. So what kind of interference is it? Constructive. All right? Constructive. Because there's no phase difference, right? There's no path length difference. There's nothing, right? Everything is just wonderful. Okay? All right. So again, they were in phase, and then they had the same path length, so no phase difference. Ah, wonderful. Okay, let's make a harder one now. I'll give you a big hint. Okay, now we want to know what kind of interference you have here. Okay, now I'll give you a hint. This wave, okay, so this wave only has to travel from here to here. This wave has to travel here to there, right? So this wave has to travel 1.5 meters more than this wave. That's a huge hint. Right, so pause your video And make sure you pause it. You have to understand this. This is a little tougher one. So pause your video and figure it out. Okay, we're back. All right, so there's a path difference, right? I mean, they're identical speakers, right? They're identical speakers, they're in phase. So what's the only difference between them? The only difference between them is that this guy has to travel 1.5 meters more than this speaker, right? So there's a path difference. Delta x is 1.5 meters. Now, what do we care? Well, what we care is how does that relate to the wavelength, right? If this is one wavelength, well, then it's going to be constructive, agree? So in other words, we've got to see how much of a wavelength this is. Well, I don't see anywhere where they give us the wavelength. They give us the frequency. But I was a nice guy, right? So V equals F lambda. So lambda is V over F. Well, the velocity is 343, right? That's just a speed of sound. Then I said the frequency is 343 hertz. So therefore, lambda is 1 meter. Isn't that nice? So therefore, if the wavelength is 1 meter, what's that? It's 1.5 wavelengths. Well, if there's a path difference of 1.5 wavelengths, or 1/2 a wavelength, or 5/2 a wavelengths, what kind of interference are you going to get? You're going to get destructive interference. Destructive interference. All right, one more. Now we're going to see if you learned your trigonometry. All right. Now we want to, okay, same thing, but now we want to figure out the interference at point C. Now let me give you a hint. So this is the path. So this speaker, this is the path length, right? The wave goes from here to here. For this speaker, it goes from here to here. So what we have to see, we have to learn that we have to calculate the path difference. So this is obviously shorter than this, right? Okay, let's do a little math. Okay, so this from speaker, this speaker to this speaker is 1.5 meters. From here to point C is 2 meters. So what's this? So you know, if you want to, you can just use the Pythagorean theorem, or you can be lazy, which is what I want you to do. So you've all heard of a 3, 4, 5 triangle, right? Whatever. 3, 4, 5. So 3 squared is 9, plus 4 squared is 16, equals 5 squared, 25, right? 3, 4, 5 triangle. Well, this is a 3, 4, 5 triangle, right? This is 3 times 0.5. This is 4 times 0.5. So this has to be 5 times 0.5. All right, 3, 4, 5 triangle. So 1.5 meters, 2 meters, 2.5 meters. All right, good old 3, 4, 5. So what's the path difference? So the sound from this speaker is going 2 meters. Hey, you're supposed to be doing this. I guess I'm doing it, whatever. The sound from this speaker is going 2 meters. The sound from this speaker is traveling 2.5 meters. What's the path difference? 0.5 meters, right? But the wavelength is 1 meter, so therefore it's a half a wavelength. If it's a half a wavelength, that's destructive. Okay, that's destructive. All right, make sure you understand that. All righty. Okay, so I said we're going to do this 3 different ways. So that's the first way, just talking about the phase differences caused by phase constant and path length. Now we want to do it the second way. So let's do it the second way. Told ya! Same thing, right? So we have 2 identical waves, except for different starting points. So that, which means different phase constants, phi 1 and phi 2, or phi 10, phi 20, whatever. And we want to let them interfere. Okay? So this is exactly what I showed you when we did the last one. Okay, what we want to do now is we want to calculate the phase difference at some time t. All right? And remember, this is the phase. So we want to calculate the phase difference at some time t. All right, let's do it. So delta phase is, let's just do 2 minus 1, okay? It doesn't matter. All right, so phi 2 minus phi 1. So this minus that, whatever. So kx2 minus omega t plus phi 2, 0 minus kx1 minus omega t plus phi 1, 0. Okay, very exciting, right? All right, so we have k x2 minus x1. Okay, the omega t's, they just go away. And then we get phi 2, 0 minus phi 1, 0. There you go. Now, remember, k is 2 pi over lambda. So we can rewrite this. Okay, we're going to call this here, let's call that delta x. It kind of makes sense, right? So let's do that. So k is 2 pi over lambda. We'll have it by delta x, right? And we're just going to call this, let's just call this, I mean, you figured it out, delta phi 0, right? Okay, so that's plus delta phi 0. Okay, and let's write it a little bit differently. You'll see why, don't worry about it. So 2 pi delta x over lambda plus delta phi 0. Now, if you've been paying attention, you should be super impressed right now. All right? We calculated the phase difference, right? Now, what did we learn about 5 minutes ago? We learned that the only way you can have a phase difference is if you have a path difference and a phase constant difference, right? That's what we went through those 3 examples of that. So there it is, right? There it is. There's the math, okay? So that's wonderful. And again, that's the path difference. Because there's your delta x, right? That's the path difference. And the next one is the phase constant difference. So that's exactly what we saw earlier. All right, so I'm going to ask you some questions. And I want you to answer them in do it in 2 ways. First, just think about it. And second, just use the equation. All right? So just think about what we've learned already. Okay. All right, if the path difference is a wavelength and the phase constant difference is 0, what kind of interference you're going to get? So you should be able to know that, right? Bang, what is it? It's going to be, first of all, it's in phase, right? It's in phase, and since this is one wavelength, it's constructive. By the way, I don't think this is possible. That's not possible, and that's not possible, right? I just put it in there. Okay, now let's do it with the equation. So if delta x is lambda, so this is lambda over lambda is 1, so we get 2 pi. That's 0, so the phase difference is 2 pi, which of course is in phase and constructive. Okay, the next one. Okay, now again, think about it. The path difference is 1 wavelength, so that means everything's wonderful, right? It's going to constructively interfere. But if the phase constant is pi, out of phase, destructive. So we know the answer from what we've learned is out of phase destructive. Now let's use the equation. So delta x is wavelength, 1 wavelength, so that's 1, so this is just 2 pi. But this is pi, so we have 2 pi plus 3 pi. So the phase difference is 3 pi, which is equivalent to 1 pi, so you know it's going to be out of phase and destructively interfere. Okay, one more. Okay, the path difference is 0. The phase constant difference is pi, so we know it's out of phase, destructive. Now let's use the equation. This is 0, so this is 0. This is pi, so the phase difference is pi. It has to be out of phase, destructive. All right, so make sure that makes sense to you. So let's just generalize. If we want constructive interference, this whole thing right? This whole thing, the phase difference has to be, 0, 2 pi, 4 pi, 6 pi, 8 pi, on and on and on. So the phase difference has to be m 2 pi. If we want destructive, this whole thing has to be, like pi, what did I just say? No. It has to be pi, 3 pi, 5 pi, so forth and so on. All right? And again, you don't have to write it like this, I mean, if we felt like it, we could have written that last one. Hold on. So this one here, if we wanted to, okay, look at what we're trying to get is pi, 3 pi, 5 pi, right? On and on and on. So, we could have said, this is delta phi. That's what we want. We could have said m minus a half times 2 pi, right? As long as we say that m is 1, 2, 3, on and on and on. It doesn't matter. See, that's what I'm trying to say. It doesn't matter. As long as you specify your m's, you can say m plus a half or m minus a half. The only reason we use m plus a half is because we wanted to use the same m's because we're lazy. Okay, let's stop.